Okay, so I'm going to talk about the relationship between forces and momentum, and we need to talk about some really important ideas here. So let's start with this guy. This is Aristotle. Aristotle. He lived a very long time ago. He was a Greek philosopher. You probably heard of him. So he looked at nature and said, I'm going to figure everything out. So he said he took things like this Lego block, which he didn't have because, they didn't invent Lego at that time. And he said, what would happen if I push that block? What? It moved. What happens if I push it and stop pushing it? It stops. So in Aristotle's mind, pushing something made it move, not pushing something made it stop. Okay? That's an important thing to realize that one, this makes sense. This makes sense that if I stop pushing it stops. So Aristotle's idea of forces is forces move. He says forces equals move. If you have no force, you have no movement. Period. He also said something else. He said if you take the block and you drop it, then it falls. Things fall. And that also seems obvious. And this is the problem with Aristotle. His stuff makes sense, okay? But it doesn't agree with the data. Now, he didn't really describe fall. He didn't say if it's falling at a faster speed or increasing speed or whatever. Because when you drop this, it's really hard to tell what it's doing. Human eyes are really good at detecting motion. We're not really good at detecting changes in speed. So does this change in speed as it falls? Well, who knows? He didn't really care. Because you know what? That's the way Aristotle rolled. And he had a little bit of hair like that. I have no idea. Okay, so next we have this guy. There were other people in between that people just forgot, and they didn't get any credit for anything. So I'm sure that there are other people involved, and I apologize to them. But these are the people that we like to think about, and this is Galileo. Galileo. Okay, let's look at this. So here I have Galileo did something different than Aristotle. Aristotle thought, hey, if I collect data, it's just going to be bad anyway, so I'm not even going to bother. So he didn't really collect data because that's not cool. He didn't want to do that. So Galileo took this track. I'm going to take a little track like this, and it's barely inclined. Let's incline a lot, like that. Now I can take this ball and put the ball right there and let it roll down. Okay, so it's moving. But if I look at this distance, right? How long did it take to do that? You can time that. It's not too hard. And then if I double that distance, does it take double the time to get there? And the answer is no. It doesn't take as double the time. It takes less than double the time. So this means that as this moves down the track, it actually increases in speed. Further, he did something like this. He put it at an even lower angle so that you can really measure that motion. And he even did it even worse. Let's say I barely incline this. Let's do it one more time. Now it's moving at a constant speed, and there's nothing acting on it. So Galileo, one, said acceleration, and two, constant velocity with no force. So he said, basically, he's saying, I don't think that Aristotle's right. Okay. Finally, we have this guy, Newton. So you may have seen what Newton's done with his 3 quote laws, and we're not gonna focus on this because it's not the main deal. But let's just write them down. Law 1. Aristotle was wrong, and you may say, "Oh no, that's not what it is. I took high school physics." It said for objects move in a straight line unless acted on by a force. So that is saying Aristotle's wrong. Aristotle said that if I push on an object, it moves. If I stop pushing, it stops. He said the natural state of an object is to be at rest. If you don't act on it, it will be at rest. And Newton says no. The natural state of a motion is constant velocity. And we've already looked at velocity, so I'll write that as a vector. constant, some value. Okay. If you leave it alone, if you don't interact with it, it will move at a constant velocity. Yes, if I don't push on this and it's at rest, zero velocity, staying at zero, is a constant velocity. Okay, so that's his first law. Aristotle's wrong. Law number 2, Newton said that the acceleration of this object depends on both the mass of the object and how hard I push it. And so that's where you see this F net equals mass times acceleration. And we'll talk about that later, but that's his second law. And then his third law says forces are an interaction between two things. Forces, interaction, two things. That's what it says. So if I have these two objects and they're both, let's say they're planets or whatever, then there's an interaction between these objects. So that this object pulls on that one, but this object pulls back on that one with the same force. Okay, so forces always come in twos. You can't have a single force by itself. Just like you couldn't have, I don't have it right there. You couldn't have a string with one end, right? Here's a string. I can't have a one-ended string. If I cut it, I get two more ends. So I'll always have two ends to a string. So that's his, the three laws. These two, you might want to combine together because this is really just not a law. This just says Aristotle is wrong. This is the relationship between force and acceleration. And this says forces are an interaction between two things. Okay, so that's where we are right now. Now let's talk about the momentum principle. Okay, so we've already defined momentum as this, mv divided by the square root of 1 minus v squared over c squared. And that, where c is the speed of light, so c is about 2.99 times 10 to the 8th meters per second. That's momentum. Now, for a lot of cases that we deal with, the objects are not moving near the speed of light, so this value is going to be close to 1, so I can say P is equal to the just m times v, because that whole thing on the bottom is just 1. The momentum principle says the following: F net equals delta P over delta T. That is the momentum principle. So first of all, what does F net mean? That means that if I have an object and I have two forces acting on it, whatever they may be, FA and FB, then F net is the vector sum of those forces, FA plus FB. So you have to add them up. You have to include all the forces on that object, not the forces that object exerts on other things. Okay, so that's the definition of net force. The change momentum, this is just P2 minus P1 over the change in time it took for that force to apply. That force was applied. And in the past chapter we practiced this change in momentum, so that's why we have it in there. Okay. Now what does this have to do with Newton's second law? Well, what if I take the limit as delta t goes to 0? If I do that, then I get this. F net equals dp dt, a derivative, right? The limit as delta t goes to 0, this becomes a derivative. And I can write this as d mv dt. Now, how do you take the derivative of a product? Well, I have to take the derivative of the mass times the velocity plus the mass times the derivative of the velocity. So I'm going to say this. I'm going to write this as d m dt times v plus m times dv dt. For most objects that we're going to deal with, the mass doesn't change. So how does the mass change with time? Well, it doesn't. So that's 0. So I get F net is m dv dt, and that is a vector. But remember that the acceleration is dv dt. So this is just going to be ma, which is what Newton's second law says. So they're the same thing for the most part. When are they different? They do not agree this is better because it works in more cases. This works even if the mass did change. It's still the change in momentum over the change in time. Okay, so it doesn't matter. This also works if you're moving very close to the speed of light. If you use this as your momentum, this still works. Okay, this ma does not work near the speed of light. Okay, so you have to take that into account. Okay, one more thing, and then I'll make another video showing something else. Let me show you what we can do with the momentum principle. So here I have F net is delta P over delta T, and that's going to be P2 minus P1 over the change in time. So I'm going to multiply both sides by delta T, and I get P2 minus P1 equals F net delta T. Now I can add P1 to both sides, and I get P2 equals P1 plus F net delta T. So this is part of our process of numerical calculations. If I want to break a problem into tiny steps, and I know this time step is very small, I can calculate the forces on the object and use that to update the momentum. So if I know what the force is after some time interval, I can find the new momentum. And then I can use that with my update position. Right? I don't need to update the velocity because it's in here. So now I can say this. Before I had this, R2 equals R1 plus V average delta T. Well, for objects not moving near the speed of light, this is actually going to be R2 equals R1 plus P2 over M delta T. And again, this is an approximation in my numerical calculation. If I use the final momentum as a measure of the velocity, I can use this to update the new position. And then we can update time. T2 equals T1 plus delta T. And then just do this over and over and over again until we get what we want. And this even works for cases where the force changes. And that's what makes this so powerful. Okay, so I'll do some examples in another video, but that's your first introduction to the momentum principle.